let's get started with the definition of a derivative. So I'm super excited about this lesson, and hopefully it will make sense for you guys. Let's start with some review. A secant line is a line that touches a graph at 2 points, okay? So I have 2 points here on my my coordinate plane. My timings are going to be a little off for this, but it should work out okay. A tangent line is a line that touches a graph at 1 point. So just like my conversations tend to make sense at 1 point and then they go off on a tangent line touches a graph at 1 point. Uno. So here's my graph. Here's my secant line touching at 2 points, and there's my tangent line touching at 1 point. The slope of a tangent line is what we are looking at today. That is going to be the derivative that we're going to be talking about, and we'll find out how to find the equation of the slope of a tangent line. So the slope of a secant line can be found, not count, but anywho, can be found by using the coordinates of 2 points on a graph. So if you remember, this is slope is represented by m, and we have 2 points on a graph. So usually we call that, man, this is all sorts of messed up, delta y over delta x, okay, rise over run, y2 minus y1 over x2 minus x1. I really hope you have your audio on for that, because there's just a lot of typos here. I didn't rush this at all. Okay, how do we find the slope of a line that only touches a graph at 1 point? So that slope equation requires us to have 2 points, but if we only have 1 point, what do? Well, that is where we use our knowledge of limits, and we can calculate the slope using only one coordinate. And of course, one is missing because, I'm making a lot of sense today. Okay, it's all about that slope. Okay, I probably shouldn't sing something pretty terrible, but let's go ahead and graph my function. Okay, I have some sort of function over here, and you see that red point? That is where I'm trying to find the slope of my tangent line. I want it to touch at that point only, so I made a secant line touching that point and touching another point on the graph. So as you can see, the slope is kind of close, but it could be closer. So I'm going to try moving the line to see if I can get closer to touching at 1 point. Okay, here's my second line, and it's super close. It kind of overlaps a little bit, so not that much of a difference. So I'm going to draw a different line. There we go. I'm still going through the point, and I'm still touching the graph at 2 points. Barely, but still doing it. I'm getting closer though, and here's another point where again I'm barely touching it at 2 points. One at my red point and the other at some other point in the graph. So I wish I could point this out, use a little pointer or something, but apparently that does not want to work. So what do you notice about the x coordinates of each line that approaches the red point? So if we look at our x coordinate from the first line that we did, it looked like it was about 3, and then it looked like it was touching the graph at 2, and then it looked like it was touching the graph at like 1.5. Okay, so we notice that our x coordinate is getting closer to the x coordinate of the red dot. So the distance between them is getting shorter. And what do you notice about the y coordinate of each line that approaches the red point? Well, just about the same. The distance between the two y coordinates are getting smaller, so that the second line of the secant line, the second point of the secant line, is getting closer to that point that we want the tangent line to touch. Okay, definition of derivative. The definition of a derivative is based off our slope definition, okay? That m is equal to rise over run. That's exactly what this is. So we have our slope as the difference of y's over the distance of x's. And sometimes we call that delta y over delta x, and it means the same thing. So here I have a line that is going to be my tangent line that's touching the graph at one point. And here's my second line where I'm touching that one point again, but this is a secant line because I'm touching the graph again when a little bit closer to where x is equal to 2 point something. It looks pretty close. My drawing isn't that great. So what I'm going to do is find out where my y's and my x's are, so I can write the slope formula. Okay. So here's my first x, right? It's at this yellow line right here, and I'm going to pretend I don't know what the value of this is. It looks like one, but I'm just going to pretend I don't know, and I'm just going to call this x. That means my y value is f of x. Okay, I hope you're with me there. So I have my x value of x, and then my y value, that is f of x. So input and output, all that part should be review. And I'm going to look at my second coordinate of my secant line. And the distance between these two x values is h. That's what I'm going to call my distance. I can see that's just a little over 1, but again, I'm just going to pretend I don't know what it is and say generally the distance between my first x and my second x is h. And since my distance between these two coordinates is h, I can say that my second coordinate is my first x plus whatever my distance is between them. So I'm going to call my second x coordinate x plus h. So there's a reason why we're going to be covering this over 2 days. I do recommend that you watch this video again if you need to. If not, then awesome. So if this is x plus h, then the y value is going to be called f of x plus h. And now that wasn't super great positioning, but hopefully you can read that okay. Okay, what happens to h when we move the secant line closer to the tangent line? So that was like our previous slide where we noticed that the distance between them was getting smaller and smaller. So that's what's going to happen with h, and I wish I could just kind of drag this and show you, but I'm not that fancy. That h is getting smaller, and we kind of want h to be like 0, right? We kind of want h to not exist, so that way our secant line becomes our tangent line. That is where our limit is going to come in. Okay, so if our slope can be written as f of x plus h, because that's our second y value, right? F of x plus h minus f of x being our first y value, I'm sorry. And then x plus h, which was our second x coordinate, minus x, which is our first x coordinate. That's the slope. And then I can write this as a limit, okay, as the limit as h approaches 0 of my slope function. Okay, so I went ahead and I simplified. If you see the denominator of my slope, it was x plus h minus x. Those x's cancel, and I'm just left with h as my denominator. And so as I can find the limit as h approaches 0 of my slope function. That's the super exciting part. That's the magic of calculus. It begins here. Okay, derivative of a function. The derivative of a function goes by many, many names, and we'll probably see more as we continue. Rate of change, slope of the tangent line, f prime of x, that's what that little apostrophe thing is, dy over dx. They all represent derivatives, which by definition is, once again, the limit of f of x plus h minus f of x over h as h approaches 0. So we immediately can tell when we plug in h just as it is. H is on the bottom, which makes this an undefined equation. That's not going to happen. Let's see this in action. Okay, find f prime of x, derivative, if f of x is equal to 3x plus 2. So we're going to write this out, and I know you see my funny little arrow there. We're just going to plug in x plus h in that, we're going to, let me rewind. We're going to write the function in the denominator and the numerator, blah, twice, okay? The first time you're going to write it, you're going to replace x with x plus h. So that is what I did in that first part, and then it is minus f of x, so you're just going to rewrite your function, and that is all over h. So I have my little arrow there to remind you to distribute your negative when you are simplifying this. Please, that should be negative 3x minus 2 when you have this simplified. I went ahead and simplified here, so you distribute that 3, you distributed that negative, and you're going to simplify. I see here I have 2 3x's that are going to cancel. My 2's are going to cancel, so I'm going to go ahead and cross them out. Now I have the limit of 3h over h as h approaches 0. But what do you know? Something else cancels out. I know you see it. There we go. Your h's cancel out. So f prime of x is equal to 3. And that one was pretty easy. Let's look at some steps to help you remember what to do for using the definition of derivatives. So I have my function f of x is equal to 3x squared plus 1. My first step is to write the limit just like the definition. Wow, lots of typos today. So I'm just going to start off by writing that, okay, with my division sign ready to go. And the numerator, excuse me, write the function with x plus h, substituting every x, then subtract the entire original function. Write h in the denominator. So I went ahead and I did that there. I wrote my function, but I replaced every x with x plus h minus my original function. So notice how I have my original function in parentheses, because that is going to help remind me that I need to distribute that negative that's going to come before it. Now I need to simplify the numerator and the denominator. Boom, I know that happened super fast. I went ahead and simplified that for you, and now I'm going to simplify that even further, because I see that there is 3x here, 3x there, they cancel, my 1's cancel, and then I'm just left with, come on now, okay, oh right, so I see that I have h's that I can cancel too, so I'm going to pull out the h from that term, pull out one h from that term, and the h on the bottom. So I'm really just left with the limit as h approaches 0 of 6x plus 3h. Now I'm going to plug in 0 for every h value. And when I do that here, I see 6x plus 3h. I'm just plugging in 0 for that h, and 3 times 0 is just 0. So my answer will be 6x. So f prime of x is just 6x. That is the derivative of this function. Let's look at some more practice. Okay, I'm looking for f prime of x of negative 2x plus 50. So the first thing I'm going to do is write it in my definition of the derivative. Okay, I'm replacing every x with x plus h minus the original function. So again, please do not forget to distribute that negative, because when I simplify it, it now becomes plus 2x minus 50. And what do you know? Things cancel. Look at that. More canceling. Okay, I'm going to rewrite that. That's a negative 2h over h. And again, canceling. Now I get to plug in 0 into nothing, apparently. So f prime of x is just negative 2. Anyway, I hope that video was helpful, and you may again need to rewatch that. I know that was a lot to digest, but hopefully that helped, and have a very good evening.